Hey, everyone. So what I want to talk about today is about autonomy and asynchrony, two concepts that I think are super important if you want to build reliable systems. And I want to talk about some of the culprits that you might have that prevent your systems to be autonomous. And I want to talk about some of what those culprits are, and of course, how do we solve them, and some gotchas that you might need to know. Not everything is all great and green, right? So I've been a software nerd for over 15 years, and along the way, I've learned a lot of things, and I will share some of my war stories with you. Hopefully, some of them are good, some of them are horrible. But I now work as a developer for particular software, the makers of NService Bus. Who here has used NService Bus or heard of NService Bus? Oh, great. So I work as a developer. I work with MSMQ, one of the transports. NService Bus is a reliable messaging platform that lets you use event-driven architecture in your systems. But before we get started, first, I want you to go on a journey with Cassini. I want you to travel 2 billion miles in space all the way to Saturn and explore the vastness and the amazing, breathtaking discoveries that Cassini made, including finding water in one of Saturn's moons, Enceladus. And what was happening was Cassini was running out of fuel. And this was concerning to the scientists at NASA because they didn't want, if left unchecked, Cassini could potentially crash into this moon that could potentially hold life. So they came up with this grand plan, the grand finale. And what ended up happening was they transmitted instructions to Cassini using NASA's Deep Space Network. NASA's Deep Space Network is an array of antennas, and they are placed equidistant in 3 locations, California, Spain, and Australia. So at least one of these centers can communicate with Cassini as the Earth rotates. So these instructions were transmitted to Cassini, and Cassini received those instructions after 80 minutes. So it takes about 80 minutes for these instructions to get transmitted. Once Cassini received those instructions, it executed 22 dips between the rings of Saturn, and finally crashing into Saturn itself, taking this last picture, transmitting to Earth. So our human brain that's capable of producing these amazing experiences and science and technology is autonomous. We have about 100 billion nerve cells communicating with each other. Part of you are wondering, what does this have to do with Cassini? Part of you right now are wondering, evaluating me as a speaker. By the way, please, I would appreciate your feedback. Don't forget your feedback. So there are a lot of things that are going on simultaneously, asynchronously, and autonomously. There's this fabulous, fantastic TED Talk. It's called 3 Clues to Understanding Your Brain. And this TED Talk, there's this neurologist who studies these patients who had injured their brains, and he was able to come up with a solution for people that were suffering from excruciating pain after an amputation, suffering from phantom limb syndrome. So if you search for TED Talk, phantom limb, you'll come across this talk. But after I watched this talk, it was incredible. I was thinking, oh my God, this is so cool. Our brain has such beautiful bounded context, and it's autonomous, and there's all these event-driven architectures and all these messages that are being passed on, and it's, taking compensating actions, and it's just wonderful. My son, he's 12 now. He got injured. He got hit in the face, in his eye, by a soccer ball. 12-year-olds. And so the injury was pretty bad. He had to be in bed rest. He couldn't see he had the Pirates patch, and so he had to be in bed rest for about like a week. I mean, try keeping a very healthy 12-year-old boy in bed. And of course, like, he couldn't see, but all his other parts of the manipulative brain are perfectly in function. Like, hey, mom, can I get sushi today? Hey, mom, can I get milkshake today? So it's great. Just because, one part of the system fails doesn't mean the entire thing goes down. Everything else is functioning in full capacity. So I want to talk a little bit more about our human experience, human child development. Now, there's a small child during, development, growth and development, there's a lot of things that's going on. There's physical growth, there's emotional growth. You can't expect one type of growth to happen first before the other happens. It all happens simultaneously. So there's asynchrony everywhere. So what is autonomy? Building autonomous systems is definitely easier than free rock climbing. That's Steph Davis. She's free soloing Scarface. But when you have, like in software, you want to have systems that are independent, that are capable of doing its job without being dependent on another. But oftentimes, we have components that rely on something else to finish its operation first before it can continue. So there's this sort of dependency that we have. Take Cassini, for example. Cassini, once it received those instructions, the instructions were actually sent April of last year. And the final crash, the dip, happened in September. So between that time, Cassini was able to execute all those instructions that was received autonomously. And it had to be able to take compensating actions. You can't always wait for 80 minutes to pass by before making the smallest of change. It had to have some kind of compensating mechanism so it can react to changes as and when they happen. So it was entirely autonomous. So asynchrony is where you have software systems that can work simultaneously, doing different things at the same time without being dependent on the other to finish. Now, in .NET, the async API was introduced as a first-class citizen, I think, from C# 5, 5.1. But again, coming back to Cassini, it was a fire and forget type of instruction. So the instruction was sent. It wasn't like the control center was waiting for 80 plus 80, 160 minutes to, they weren't blocked. It was like, send these instructions and then continue with other things while Cassini received those instructions and did something else. So there's this whole fire and forget notion. If you think about Amazon, like when you're placing an order, for example, you place an order. The fulfillment thing could be down completely. It doesn't matter. But Amazon just sends you an email, says like, hey, we've received your order. Your order will be fulfilled shortly. And then whenever the fulfillment system comes back up, it completes the order. So this sort of this fire and forget gives you that ability to make your systems more performant. So I grabbed this code from a WCF sample from MSDN website. And this is fairly simple. It's a WCF service. It's newing up a calculator client, and it adds some result and returns a value. Can anyone tell me if you can spot any design problems with these lines of code? Sorry? No, forget about the syntax errors, or sorry about that. But it's hard to test, yes. The bigger design problem here is that it hides latency. So the add method takes the two operations and then gives you the result. But this is a service, and this service could be running locally, or it could be running in Cassini, and depending on where it's running, the result could be instantaneous, or it could come back 160 minutes later, or a long time later. So this line of code, it assumes that latency is 0. Now, this is a crazy story. This was many years ago. This was back when I believed calm is love, and this is one of those projects where it was a huge set of developers in the back end and a small set of developers working front end. It was a waterfall project which had taken a whole year and something just to produce the specifications, which was in a nice boundar that was like handed over to me when I joined. After 7 or 8 months later, we completed that. It was, the UI was pretty and it was great. And then we tested it. We ran it against live production type data. And it took 8 minutes for the results to come back. 8 minutes, 8 whole minutes. Now, if Earth and Mars were aligned, we could have sent a message to Curiosity. We could have said, hello, Curiosity, how are you? And we could have received an answer back from Curiosity. I mean, that's how long it literally took. So we had a lot of postmortems after that. And we found out the reason was, there was a whole bunch of reasons. We had used Corba, and we had used XML because somebody there higher up hated Microsoft technologies. So people were making all kinds of crazy choices. And in the end, it was really very chatty calls that was going back and forth between the front end and back end. And there's a whole bunch of serialization going on back and forth. And it was adding a lot of time. It took 8 minutes, and sadly, after spending close to $7 or $8 million, the project got canned. And it was very unsatisfactory. You kind of get the horrible feeling. You worked on it for 8 months, 9 months, close to a year, and then the thing that you thought was great, it just didn't work in the end. And it was because of latency. The other problem that this also hides is network reliability. One of the first fallacies of distributed computing is that the network is reliable. How many of you here have had some network issue one time or the other during development, testing? Yes, me too. But when we write code, sometimes we don't see that when we write code. We assume that the network is reliable. In a previous company that I worked at, we used to have this term called you have to IT-proof your code, which just meant that our network wasn't very reliable, so you have to make sure you have retries in your code just in case it fails, your retry attempt would catch it, which was great. At first we were thinking our IT, wasn't that great, but it's just how it is. Network is not reliable. So when you think about the fact that network is not reliable, latency is not zero, you tend to add better design in your code. So we added retries. So the thing about retries is some operations are easily fixable with retries. Network glitches, and if you have like a database deadlock exception, the database deadlock exception even tells you, please retry this operation because I'm sort of busy at the moment. So, so when you retry, these problems go away. But then you have some operations that you can't possibly retry. What if you are doing credit card charges? You can retry 5 times, but your customers may not be very happy with you. But then again, when you think about these things during design, you can take decisions based on how your code should react. What if there was a card failure? Is there a business policy that that needs to be accounted for? So you start to think about these things and what sort of compensatory actions that your business might want to take, and then proceed accordingly. But then when you consider this, so it kind of forces you along these good design principles when you consider latency and reliability. So coupling. Coupling is kind of sort of like a bad word, I'm sure. But in general, it's a measure of dependencies. So let's say you have a component A, if you make a change to this component, how many other components are going to be impacted by this change? So that is coupling. Some coupling is necessary, that you could have a coupling on like your infrastructure, what kind of logging framework you use. I mean, it is essential. But sometimes coupling can be bad, and there's this type of coupling called temporal coupling, which kind of prevents your code from being autonomous. So to talk about temporal coupling, I want you to imagine this. It's a very busy morning, and you are dying for your coffee, and you're going to Starbucks. And the line is extremely long, and it's moving very, very, very slowly. But you persist because you want your coffee. You finally get up to the front of the line and then place your order. And this is what happens. So the cashier gets your order, and then he walks to the barista and repeats the order and just stands there and waits as the barista makes the coffee. And waits and waits and waits. And finally, when the barista is done, brings back the coffee to you, and then charges the money from you. I don't know about you, but that would make me very angry. So if we take temporal coupling, temporal means dealing with time. And coupling, as you know, is a measure of dependency. So when you have two services that are dependent, so in this case, you've got the cashier service and the barista service, and the cashier service cannot complete its final operation because it's waiting for the barista service to complete its operation, you have temporal coupling. So when you have temporal coupling, you don't have autonomy. And when you don't have autonomy, it's hard to scale because you have the resources of the cashier service that are held in waiting. They're blocked in waiting. So in a situation like this, it becomes super hard to scale up these things. When we were looking originally, very long time ago, in a previous company that I worked for before joining Particular, we were evaluating different things, including BizTalk. Oh my God. But the reason why we were looking at it was there was this legacy system, and it was doing great, but it had maxed out. But of course, the company had made a lot of money on it, so they just wanted to throw more money so they could, get more money. But the thing is, like, because of a whole bunch of temporal coupling, there's only so fast you could go unless you go and fix these things. So this really kills your scalability. So how do we solve for it? Again, if you take it real life, Starbucks to the rescue. So when you order, what happens in actual Starbucks is that the cashier takes the money from you, the cashier charges you, and writes the information on the cup, whatever you ordered, places it on the queue for the barista, and then moves on to the next customer. Here, if you look at it, the cashier is doing what a cashier is supposed to do, which is get your money, charge you for it. And the barista is doing what the barista is supposed to do. And then when the barista is done, they call out your name. But until then, you're free to do whatever you want to do. Check your email, check your Slack, and respond to so many other things until you get your coffee. So if we were to translate this, again, to software, we would use a pattern called publish, subscribe, and we would use messaging. Now, publish, subscribe is just one of the more than 100 patterns described in the book Enterprise Integration Patterns by Gregor H. and Bobby W. I do not want to pronounce their last names. But it's a great book, and it's just one pattern. But essentially, if we use that pattern to what we had before, we would have the same two services, cashier and barista. And the cashier would receive the message and process the message. And then when the cashier transaction's done, would publish an event, drink ordered. And you could think about this as the cup that's been placed in the barista's table. The barista is subscribed to it, and therefore receives this message. And then the barista performs whatever the barista needs to do and sends an event. So this is more real world. And there is no crazy need for polling. The barista does not have to keep polling the cashier, like, hey, do you have any drinks for me? Hey, every 5 seconds or a minute. the message is received by the barista as and when it happened, and the barista can process. Now, in this model, you have removed temporal coupling, and now you have made these two services completely and entirely autonomous. For example, if for some reason the barista service were to go down, it doesn't matter, the cashier can still keep processing these requests. And I mean, think about real life. The barista can undergo a shift change. You get new baristas in. That doesn't stop the cashier from helping customers. Same thing, if the cashier service was to go down, it still doesn't matter. The barista is going to keep processing all those messages in the queue and continue to do so. So having one part of the system down has no impact on the other. They are both fully and entirely autonomous. The real cool thing about when you achieve this is you can scale up. Suppose there's a long list of messages for the cashier. You could spin up multiple instances of the cashier to fill that load pretty fast. Same thing for the barista. So you have all of that because you solved the temporal coupling problem. So event-driven architecture is just a style of architecture where you have all these components and they communicate using messages and events. Events are just messages. So they use these messages to communicate, to talk to each other, to let them know what happened. So it eliminates the whole need to poll. So systems react in a more organic way as and when things happen. Now, you need sort of something, a transport, to take these messages from one place to the other. That's where queuing comes in, queuing technology. You've got different transports. If you're running on a native Windows, you still have MSMQ. MSMQ is still alive and kicking. If you're on the cloud space, using Microsoft technologies, you have Azure Service Bus, you've got Azure Storage Queues. If you're in the Amazon space of cloud, you have Amazon SQS. There are RabbitMQ, of course. So you've got all these different queuing technologies. So, and then there are event buses, and Service Bus is one. And Service Bus is just an abstraction that sits on top of these queuing systems, so it can deliver those messages, take heavy lift some of those things that you would have to do yourself, such as retries and so on, with all the receiving stuff that you have to do. And Service Bus is just one. You've got Mass Transit, which is open source, and then I think there's the new kid on the block, which is Jasper from Jeremy Miller. Jasper is brand new. I think it's still in alpha. You'd have to check it out. But you have these event buses that kind of help you so you don't have to talk to these queuing systems from scratch. So you've got something that shuttles messages, and then you have queues. Queues in real life is horrible. Nobody wants to stand in the queue. But queues in software is great. It helps you get rid of temporal coupling so your code can be autonomous and can scale. So queues, you can think of queues as the barista's desk, for example. It's just a place where you store things. So queues are where the messages go, and they're persisted on disk. So queues help you with the whole reliability aspect of it. So when one system goes down, the messages are still persisted durably in the queues. So when the process comes back up, it can pick up those messages from the queue and can work on it. So it gives you that reliability. And so event-driven architecture is great, but we all sometimes, a lot of times, deal with legacy code. And legacy code is fabulous. Like I said, the company probably made a lot of money on that software. They just want to throw more and keep it going. But it could be such a big pain. And it's a pain to go in and fix bugs, because by fixing bugs, you don't want to break something else. And of course, the business has to expand. So there's all these new feature requests that are coming in. So you've got to carefully work around that area of how do I do this without having to regression test my whole system. And sometimes there are no proper tests because it's legacy, and you probably are seeing this code first time, and this has probably been around for more than 5-6 years, so this is beyond your time. But every developer kind of goes through this. Oh my God, this sucks, and we should rewrite this. But rewriting stuff is hard, and when you're dealing with a very large system, you could just be making the same mistakes and with the new technology of today. So it's kind of hard. So I want to share, this time not a horror story, but a happy story of how I've used event-driven architecture to solve some of this. So there was this problem where we had, this is again my prior experience, we had priority customers, and they would drop these CSV files, and we would process them. Each line would correspond to something that got shipped. But each line needed to go through a lot of customizations and transformations and a long list of processes before this thing got shipped. So, but it being legacy code, we had zero visibility. And of course, like the SLA started to get too close. We were we didn't violate any SLAs, but it was like a nervous thing. Oh my God, this took so long. So we were asked to look at it. So what we did was we took this monolith, we carefully looked at all the important parts, and then we instrumented it with events. So instrumenting it with events is just like going to the place and said, OK, this is done step A. So whatever that business step at that time was, it completed. So we would go into all these places where something of significant business thing had completed, and we would just publish an event. So we later added a subscriber that would listen to all these events, and then we were able to see what step of the process took too long. And all of a sudden, we had visibility. We knew that, hey, step A is happening really fast. So when we narrowed down, we found that there was a computation step that was taking a long time. It was it was a billing service. This service was actually a local WCF service, so it wasn't even like a third-party service. It was something local written. And it was calculating something, and it was writing the value in the 100th field of this very important table. As you can tell, the database was also large, and it was crazy. So we looked at it even more, and then we found out that nobody was using that value, that hard calculated value, because the billing systems had undergone change, and they had eliminated that, but nobody removed that call. So every line in the CSV was making that call, that unnecessary call, which was taking a compounded effect on the whole thing. And our fix was very simple, thankfully, which was removing that offending line of code, but it gave us 30% extra. So that was really good. And the cool thing that you can do here, I think, in my opinion, is you can add new features completely on the outside. You no longer have to work inside the legacy system. For example, let's say your company wanted to try out a new promotion, right, for their priority customers. So because we have an event when the client became preferred, we could simply add a customer promotions service that listens to this event completely on the outside as a separate small thing. So the advantage of doing that is that it can receive this event, and it's completely on the outside, so you don't have the same constraints that is inside your legacy code. If your legacy code, you can't upgrade the version of C#, or it doesn't matter, the database, it doesn't matter. By writing it on the outside, you can use whatever you need to make this work. It doesn't even have to work with the same database. You could have a key value pair database or a document DB. It doesn't matter. It gives you that flexibility. So you don't have to touch the legacy code. And that's huge, because by you not touching whatever is inside the legacy, you save yourself a whole bunch of regression tests that you would otherwise have to do in your QA, adding to your QA time. So that's really great. And but event-driven architecture is not all, fun. I mean, it's fun, it's amazing, but you have to think about some of these gotchas. So with messaging and event-driven architecture, you don't have to receive the messages in the same order that was sent. When you send messages, you could have sent them in a specific order, but when you receive them, you can't expect them to be in the exact same order it was sent. So you could receive them out of order. So let's say you've got a service that handles these two messages, submit order and cancel order, and the submit order is pretty simple. You get the message, and then you create whatever it is, and you store it into the database, and the submitting order of the system is done. If you look at, let's say, the cancel order, when you receive the message, you check. You get the order information from the database, and then once you receive it, if it's around, then you perform whatever you need to do to cancel the order. So I said with messaging, these can arrive out of order. So what if you got the cancel order message first? So what are we doing here? Here, we're checking. So at this point, the submit order hasn't come in, the cancel order has come in. But we haven't seen that order in our system, so there is nothing in the database. Like very good programmers who are always taught to check for null, by checking for null here, we didn't find the order. So from this message's perspective, from this processing perspective, this message is done. It's gone out of your system. So now you get the submit order, and now you add the order in your system, and then it goes through the fulfilling process. But then the customer is upset because, according to the customer, they've canceled the order, but you have no trace. So you could solve this in a couple of ways. You could not check for null and just let this code throw an exception. By doing that, the exception happens, and then you retry. And the good thing about queuing is these transports have some way that you can poison a message. So that's a concept of saying, like, hey, if I've tried this thing 1,000 times and it's failed for 1,000 times, the chances of it succeeding the 1,001st time is pretty low. So in that case, you kind of like quarantine that message to a separate queue, which we say we could quarantine it to a poison queue or an error queue. So you kind of like say, hey, remove this offending message out. So this cancel message would be sitting in the error queue. And then the submit order would come in, would enter the system. But you are watching these error queues, so you saw that the message happened. The real cool thing with messaging is you can simply take the message that failed and retry them. So you could just take that message from the poison queue, error queue, and you could put it back to the service that was handling it. And now, because the order is already in the system, you go through the cancellation. So that's just one way. But this sort of race conditions usually means there's like a hidden process that the business probably has. Like if you think about Expedia has a 24-hour cancellation policy for making reservations, and I've used it plenty of times. I've made flight reservations for the wrong date and canceled it, and I was like, thank God I was able to cancel it. So this is pattern called sagas, and this is part of in-service bus, but this is really just a messaging pattern. And here it lets you handle multiple messages together. So here we're saying that, hey, there are two. There's a submit order message, there's a cancel order message, and there's this aspect of 24-hour time that I want to model. And because this is a business process, usually processes carry some state. So the saga data, like the order data, is just a state information. That's just your class, where you're holding information about what happens when you received a submit order, what happens when you received a cancel order. So when you could do things like after 24 hours elapses, then you could check your state object and see if you've received a cancellation. If you've received a cancellation, great. You don't do anything. You don't process the order at all. But after 24 hours has elapsed, If there's no cancellation, then you go ahead, fulfill the next step of the process. So you've really eliminated the race condition, and then you've thought about the business aspect, and you were able to model like a little bit more of what used to be a race condition is now a business policy implemented that you can take compensating actions on. So the thing about messaging is, so the first gotcha is like out of order messaging. The second gotcha is like the whole reason why we went this route is we wanted to get rid of temporal coupling. But you could add coupling by the actual message schema. So the schema of the message is like the sender of the message and the receiver of the message has to share the same schema so that they can understand. When a sender sends it, the receiver has to understand what that message is. So they share the same schema. Now, when your schema, you can think about the schema as like a simple DTO. It's just a simple class with some information. That's it. So when you start adding like more and more and more information in this message, now all of a sudden, instead of like a very small message, a big gigantic thing is now being shared, you've essentially coupled yourself based at the schema level. So that's something to be aware of. And what I've learned in the past is like I've made mistakes and oh wait, this is supposed to help me, not hurt me. But so the things that have worked for me are like I use IDs. Share IDs, not a whole bunch of information about the event. Usually have like the event date. And this one's hard, which is naming the event. As programmers, we tend to name things after the technology and the technical process of what happened. For example, PDF document generated, or when we are first new to messaging, we say command sent, or has no business importance. So if I take that event or message and to my business person and said like PDF document generated, command sent, they wouldn't have clue. But if I had said order generated, that makes sense to them. The advantage of using business language in these events is that later on, business comes to you and says like, hey, go do this promotion or whatever, when order has been accepted, or when they talk to you this way, because your system already has these events, it kind of like you can connect the dots much better. You can add a subscriber, which can implement these new things. It helps you extend your system according to the business needs. So you get that as an added advantage. Yes, naming things is hard, is one of the hardest things to do, but it's worth spending the time on naming things. I've seen so many message names, including command send. It's like, what is command send? After a few days, you have no clue what command that was, and being explicit in your naming definitely helps. And this is a huge problem in messaging, which is being idempotent. Being idempotent is the ability that you can retry something without any side effects. So if I take a message and then I process it, the first time, it should give me the same result. If I take the same message and do it 3 times or 5 times, it should still give me the same result without any side effects. So some operations are inherently idempotent. For example, let's say you're changing your address. It doesn't matter how many times you process the message, your street name is going to end up exactly the same, even if you process it 20th time. But credit card transactions are a different story. You can't do that 20 times without having very bad side effects. So this is where what transport or what queuing technology you use becomes like a big thing. Now, again, every transport's different. So regardless of which, like if you choose Rabbit or if you choose Azure Storage Queues or Service Bus, it doesn't matter. You have to know the ins and outs of that transport. Now, MSMQ supports distributed transactions. What does distributed transactions mean? It means that multiple resources can participate in the same operation, in the same transaction. So let's say you get a message, and part of that message is you're saving some information in the database. That's the database resource. And then let's say you publish an event. That's from the queuing side. So all these participate in the same transaction. So in case of MSMQ, let's say the processing fails, then the whole thing will roll back. But you've got transports which don't support distributed transactions, like Rabbit, in which case it doesn't matter. If you save information in the database, and then you publish an event, and then right when the transaction was about to get completed, something happened and the process died, guess what? The database will roll back, so there won't be any order information stored, but Rabbit would have published that event. So now your system is in an inconsistent state. This whole thing was supposed to help, not hurt, but you could end up in a world of hurt because you've published an event for which there is no information in the database. And the thing about publishing events is like you do that once something is done. It's like your statement of truth, because you have so many other downstream things that depend on this event that need to go and take actions. So this is like a ghost message. So you've published an event, and all these things are like trying to take actions, but there's no relevant information in the database. So you could end up in a bad state. So how do we solve this? There's this pattern called the outbox pattern, and where what you could do is you have a copy. When you see a message, you store all of the successfully processed messages in a persistent store for a small amount of time. So when a message comes in, you first check that collection to see if you've seen that message before. If you've seen that message before, you discard because it's a duplicate. Otherwise, you process it, and then you store it in that persistent store. Of course, it sounds simple, and the devil's always in the details when you're trying to deal with distributed transactions and idempotency. But this is a huge thing to be aware of, to know your transport's limitations and solve for. So you've used messaging, and you've dealt with. But how do you debug this? When you're using messaging, debugging is important. This is where auditing comes in. And when you audit every successfully processed message, then it's great, because now you know what messages have been processed. And at Particular, we came up with a whole bunch of visualization tools to help with this. And how we did it is we looked at all the messages that have been successfully processed, all the endpoints that processes these messages, send all their audit messages to one queue, and our software reads all the messages and retrieves information from the metadata, like headers. So we're able to, based on correlation ID, we know what messages go together, and we were able to build this message flow diagram. And so because we know things like which is the destination of this message, and who sent this message, and where it's going to from the headers, we can build sequence diagrams. And when I talked about the sagas, we have the state diagram. So if you don't have this, then you have to rely on logging. And when you have really good logging, not just logging exceptions, but actually capturing the state data, and then you can make meaningful information of like what happened to my message and where did it go. But these tools, or having an idea of like what you would need when you're going to messaging, is something that you need to keep in mind. So deployments are great, and when you're talking about breaking things into smaller components, once again, it's great because they're autonomous and scalable and great. However, if you are dealing with your company, and I hope you're not in silos with your IT ops guys, and if the process of deployment is currently not smooth, before you go ahead with messaging and before you go ahead with anything, I would say take the time to fix the deployment, to make it automated, to reduce the pain of IT ops. They're great, but oftentimes we don't talk to our wonderful IT ops friends, and that's not good. So once you've taken care of that pain, where deployment is no longer a concern, then this sort of like deploying a lot of small components is fine. But if you don't solve that problem, they're not going to like you very much. Because instead of one thing, we had this process where we had to give a detailed instruction sheet of what service needs to get deployed and what were the database changes. I mean, it was like a document that this IT ops person had to follow step by step and do it manually. So doing that for one service was pain enough. And if you make them do it 20 times, they're not going to like you at all. So fix that problem first before you move to something that's going to break your system into super small services. But when you do, things become easier, which is, let's say you've got this module, 1.0, and you want to make a small change. You can, in fact, deploy it while the 1.0 version is running, and let both these services process these messages, and see, and let it run, and watch the poison queue. Make sure that nothing's gone wrong. If everything is great, then you can go ahead and then stop your 1.0, and at that point, your new version is processing all the messages. The one thing to know is make sure that these two versions are backwards compatible. So don't make any change that is going to break like the schema, remove fields and things like that. That could potentially break your backwards compatibility. So if your change is backwards compatible, this will work. Of course, when has everything gone very smoothly in production? We've all had our moments where we've had to roll back. So let's say you do this, you deploy 1.1, but when the message is processed by this, it doesn't work. The poison messages go to the error queue. So at this point, you stop this. You simply take the messages that have been poisoned from the error queue and play it back to your old running version. So nothing's lost. Everything is still working as it should. And once you figure out the problem, where the problem is, then you can go ahead and redeploy, follow the same process. So the big thing about this event-driven architecture and messaging and breaking things into small pieces is monitoring. Make sure you monitor your systems. Make sure you monitor, especially the error queue, because you want to know when something's landed there so you can take actions. So there are several metrics that you can monitor. Like, for example, queue length. You want to know if there are 15,000 messages or just 15. So sometimes 15,000 messages is perfectly fine, but as long as you know that, that's good. And how fast are your messages being processed? And how long does it take to process individual messages? So your throughput, your processing time. Are there a lot of failures, and are you retrying a few times just to make it succeed? Could that indicate a problem? So these are all the things that you can monitor. The critical time is how long did it take for the entire thing, for this message to get processed. From the time it was delivered by the network into the queue, to how long did it wait in the queue to be picked up by your process to process it, how long did it take to process the actual message. So that's like the end-to-end time. And that's important because once you know that, and if that critical time is taking really long for your endpoint, it means that you could scale it, or you could do one of many things there. But at least know that these things are happening. So I know I've talked about a lot of things, and I want you to take away two things. One is, autonomy doesn't just belong to Cassini. It can also belong to the software systems that we write. And so strive for autonomy. Look at the places where you think that you have temporal coupling today in your code. And event-driven architecture is not the Molnir. So you don't have to use it everywhere, but use it where it makes sense. If you have temporal coupling, use queues, use event-driven architecture to reduce that. And of course, embrace asynchrony by using messaging. So this is the Twitter board. I don't know how many of you have had a chance to see it around. And this gives the top list of tweets. If you use hashtag DDD EU and you've been tweeting a lot, your name might appear here, and you could check out on the boards. This was implemented using N-Service Bus. My colleague Ramon, somewhere here. Hey, Ramon, hey. So he set it up. So if you have any questions, we implemented this using messaging and N-Service Bus. So we will be available in the open space, and you can come talk to us, and we'll be more than happy to share with you the architecture. And finally, here's a link that you can go to access free advanced Udi's course on advanced distributed design. This is a fantastic course. I kind of like started out with Udi's podcasts and videocasts and things like that before I got into event-driven architecture. I found it of huge value way back 6-7 years ago when I started. But it's fabulous, and here's how you get to it. Go to particular.net/DDD EU18. Sorry, it's HTTP and not HTTPS. Apologize. But before I wrap up, when you leave the room, I want you to leave the room with one thought. What would happen, and by the way, please do this in QA and not in your production. So what would happen if you were to randomly recycle your most important service or bring your database down for like a minute or two? Again, do this in testing and not in production. So I just want you to think about this and how your systems will behave. Thank you so much. Appreciate it.